All right, let's dive in. We're going to talk about running Kubernetes in the real world. Moving past the simple hello world stuff and getting into the nitty-gritty, the tough problems that pop up when you're actually in production. We're talking about taking that potential chaos and wrestling it back into control. And this quote just nails the central problem, doesn't it? Kubernetes is supposed to make everything simpler, but once you're running it at scale in production, it can feel like it's creating a whole new set of challenges. It's this weird paradox. So let's figure out how we fix that. First up, let's talk about traffic. You've got all these amazing apps running inside your cluster, but how does anyone from the outside world actually get to them? You basically need a digital doorman, someone at the front door who knows exactly where to send everyone.
It really is the first question you have to answer. Your services are humming along happily inside the cluster's private little world. So how does a person on their laptop or their phone actually connect? This is where that doorman concept becomes so important.
And that doorman has a name. It's the Ingress controller. Think of it as the single official front door to your entire cluster. It takes all the incoming requests from the outside world and acts like a super smart traffic cop, directing every single request to exactly the right service inside.
Okay, so we're letting people in, but, just opening the floodgates isn't a great strategy. What happens if you get a massive spike in traffic? Maybe your marketing campaign went viral, or maybe it's something less fun, like a denial of service attack. Either way, you'll crash your app. We have to control the flow.
And here's how we do it in practice. It looks like code, but it's really just a simple rule. This little snippet here is telling our Ingress controller, hey, only let 10 requests per second through. That's the 10R/S part. And for anyone else who shows up, turn them away with a 503 error code. It's like telling our doorman, the line's full, tell him to come back later.
And this is what happens when you try to push past that limit. Boom, you get this, 503 service unavailable. The first few requests got in, but all the extra ones are politely but firmly rejected. Just like that, with a few lines of configuration, we've protected our application from getting totally overwhelmed. All right, our traffic is under control. Now for the next big question. Where do your applications, your pods, actually live inside the cluster? A cluster is made up of all these different machines, some with special hardware, some without. You can't just toss your pods in there randomly. You need a smart placement strategy. The best way to think about this is to imagine the Kubernetes scheduler as a really good office manager. It knows which desks have those fancy GPUs, it knows which floors have extra security, and its entire job is to take each employee, each pod, and put it at the perfect desk where it can do its best work. Now, this office manager uses two main forces to get the job done. On one side, you have Node Affinity. That's like a magnetic pull. The pod says, hey, I really want to run on a node that has a GPU. But on the other side, you have Taints. That's the opposite. It's like a force field. An expensive GPU node might say, stay away, unless you're special, you can't run here. This is how you keep your regular, everyday pods off your specialized hardware. So if a node has a keep out sign, a taint, how do the right pods get in? Well, they need a toleration. This is basically the special access pass. If a pod has the right toleration, it can waltz right past that force field and get scheduled on the restricted node. It's the key to the VIP room. And these keep-out signs come in different flavors. No schedule is pretty straightforward. No new pods get scheduled here. Prefer no schedule is a bit gentler, more of a suggestion. But no execute, that one is the bouncer. It will actively kick out any pods that are already running there if they don't have the right access pass. Super useful for things like maintenance. Okay, we've got our pods running in all the right places. But what about their memory? What about their data? Pods, by design, are temporary. They're like little sticky notes. When the pod goes away, everything inside it vanishes. But real apps need data that sticks around, which brings us to storage. This is honestly one of the biggest hurdles when you start working with real, stateful applications in Kubernetes. If your container crashes and a new one starts up, its internal memory is wiped clean. So if you had a database in there, poof, all your data is gone. So how do we solve that? Well, Kubernetes gives us two main options. On the left, you've got ephemeral volumes. Think of these as scratch paper. They're useful for sharing temporary files between containers inside a single pod. But as soon as that pod is deleted, the scratch paper is thrown out. On the right, though, we have persistent volumes. Now, these are the real deal. They're like a sturdy external filing cabinet. The pod can go away, but the data in the cabinet stays put, safe and sound.
And what's really cool is how you can use that filing cabinet. Look at this example. We have one pod with two different containers, one for the database, MySQL, and one for the web server, PHP. They're both using the same persistent volume, but by using something called subpath, they're using different drawers in the filing cabinet. The database files live in one folder, the website code lives in another, all perfectly organized in one persistent spot.
So, we've got traffic flowing, pods running in the right spots, and our data is safe. Now it's time to make our apps tough. We need to make them resilient and secure. It's time to hire a bodyguard and a medic for our system.
Let's start with the medic. In the world of microservices, one little service failing can cause a domino effect that takes down your entire application. A circuit breaker is a pattern that stops this. If it sees that a service is failing over and over, it just trips the circuit. It stops sending traffic there for a little while, giving the broken service a chance to recover.
And here's a really nice, user-friendly way to use that pattern. Instead of your users just seeing a scary 502 bad gateway error, this little bit of config says, hey, if you see that 502 error, just redirect the user to this friendly maintenance page. The system protects itself, and the user doesn't get a confusing error message. It's a win-win.
Now, for the bodyguard. Security has to start with identity. Who are you, and are you allowed in? Now, you could build a separate login system for every single application you deploy, but that would be a nightmare. Instead, we use Single Sign-On or SSO. It centralizes everything. One identity for the user, one place to manage permissions.
Okay, I know a screen like this can look a little intimidating, but what you're really looking at here is the engine that makes SSO work. You're just setting up the rules for a secure digital handshake between your app and the identity provider. It's how your app can be sure who a user is without ever having to handle their actual password.
SSO is a really important tool, but it's just one part of a much bigger, modern security idea, zero trust. The old way of thinking was like a castle with a moat. If you made it past the outer wall, you were trusted. Zero trust completely throws that idea away. It assumes there are threats everywhere, both outside and inside your network.
It all boils down to these three simple but powerful rules. 1. Never trust. Always assume a breach. 2. Always verify. Every single time someone tries to access something, you check who they are and what they're allowed to do. And 3. Continuously monitor. You log everything, you inspect everything, and you're always looking for trouble. It's about being constantly vigilant.
So we've gone through rate limiting, pod placement, persistent data, circuit breakers, and zero trust security. But here's the most important thing to take away. These aren't just a random collection of cool tricks. They're all connected. They're all pieces of a larger strategy. So the real question is, how do you start weaving these patterns together to build systems that aren't just running, but are truly robust, resilient, and secure enough for production?